Welcome back! Today we're going to talk about more NP completeness, specifically the traveling salesperson problem. What is the traveling salesperson problem? Typically, this problem is thought of as an optimization problem. Given some graph G, with distances between each pair of nodes, that means that it's a complete graph, what is the shortest tour or cycle that visits every single node? In order to present a solution to this problem, we would give some list of vertices that would specify our cycle. Maybe in this case, A, C, B, E, D, signifying a path that starts at A and ends at A, creating a cycle, but that visits each of the other nodes in that order. The trouble with the optimization problem is this. Even given this certificate, this description of an answer, it's still fairly tricky to check whether this answer is the best answer. We would really have to explore every single other possible cycle, maybe using certain heuristics to help us in order to validate that we couldn't do better than this. To help make a decision problem out of this, we're going to add another constraint to our problem. The traveling salesperson decision problem goes like this. Given a graph G, with distances between each pair of nodes, as before, and some number k, does there exist a tour or cycle through all nodes that has combined distance less than or equal to k? So for instance, I could set k to 30, and if I noticed that I had some particular cycle here that was given, I could add up the distances on all of these edges, 5, 6, 8, 2, and 9, and observe that these sum to 30, and thus we satisfied our constraint. In this case, our certificate has allowed us to check our answer. This is an important property that we want to have in order to show that our problem is in NP. Ultimately, our work for today is going to be showing that the traveling salesperson problem is NP hard as well, making it NP complete. To do that, though, we're going to first direct our attention to Hamiltonian problems. Let's start with directed Hamiltonian problems. One such problem is this, the directed Hamiltonian cycle problem. Given some graph G, in this case you see this here, with directed edges, but no weights on any of the edges, does there exist a cycle that contains each vertex exactly once? That is, can we find a route through this graph such that we visit every single vertex and start where we ended? This type of problem was something that William Rowan Hamilton was particularly excited about, and thus created a bunch of problems using islands and bridges between them as brain teasers for people. However, this problem existed long before its namesake, Hamilton. In fact, Rudrada was interested in movements that different chess pieces could make, and studied problems very connected to this in the 9th century. We also have the directed Hamiltonian path problem. This is quite similar to the directed Hamiltonian cycle problem, except instead of looking for something that starts and ends in the same place, we want to visit every single vertex exactly once, but we're okay ending without revisiting our starting node. Obviously, if you have a Hamiltonian cycle, you can turn that into a Hamiltonian path by dropping that last edge that you would take. However, we're going to be interested first in talking about the directed Hamiltonian cycle problem, and specifically showing that this problem is NP hard. It's already fairly evident that this is in NP. We have the same type of answer checking that we can do in Traveling Salesman, where we list the set of vertices that we want to use to construct our solution. For instance, A, B, D, E, and C. And then we double check that our route visits every single vertex, and that every single edge that we would need to exist actually does exist. So, how do we show that this is NP hard? We want to pick some problem to reduce from. Intuitively, we might pick some problem that shares the fact that it has a graph involved, and additionally this idea that we're trying to find something that minimizes in the traveling salesman problem case. But in the Hamiltonian cycle case, it's not clear that we're either trying to find something that uses as few vertices or as many vertices as possible. We need to visit every single vertex. So intuitive things like vertex cover or independent set from the graph pool aren't necessarily the most obvious. In our work today, we're going to use 3-SAT instead. Technically, both of these reductions are possible. Both are fairly elaborate, and they aren't the sort of thing that I would expect you to be able to reproduce on your own for a homework problem. In order to introduce you to how this reduction works, from 3-SAT to directed Hamiltonian cycle, I'm going to show you some interactive slides that I encourage you to walk through step by step. They show how you build up a graph that corresponds to a Boolean formula, such that if that formula is satisfiable, then this graph will contain a directed Hamiltonian cycle. At this point, I'd encourage you to pause and go look at that slide deck yourself. Once we've shown that directed Hamiltonian cycle is NP-hard, we can talk about lots of other flavors of Hamiltonian problems. For instance, we might be interested in cycles, or we might be interested in paths. Maybe our graphs are directed, or maybe they're undirected. Maybe we want to be able to specify in a Hamiltonian path problem what the specific endpoint should be, the start and end of our path. We're going to look at a couple examples of reductions that we can do now that directed Hamiltonian cycle is part of our pool of NP-hard problems. We'll start by reducing from directed Hamiltonian cycle to directed Hamiltonian path. The first thing we're going to do is we're going to select some vertex. In this case, we'll select vertex E from our original graph. Our goal in doing this is to create a graph based on the original graph, such that if there was a directed Hamiltonian cycle in the original graph, there will now be a directed Hamiltonian path, but if there wasn't a cycle, there can't possibly exist a Hamiltonian path. When we pick this vertex E, what we're going to do is copy it. That is, we'll make a new vertex E' that has the same incoming and outgoing edges as E. We're then also going to introduce two other new vertices, S and T. S is going to be the intuitive starting point of our directed Hamiltonian path. So we'll have an edge from S to E, and then for our ending point T, we'll have an edge from E' to T. Intuitively, we want it so that if there is a directed Hamiltonian cycle in the original graph, that will correspond to a directed Hamiltonian path that starts at S and ends at T. If there is a directed Hamiltonian path in our new graph, we know that those have to be the endpoints. Otherwise, we wouldn't ever be able to reach S or T. First, let's quickly verify that this took polynomial time. In this case, we introduced a total of 1 vertex and 4 edges. In general, it's possible that we might have to introduce more edges, but effectively this isn't going to take more time than the number of vertices in the graph, which is the total out degree and in degree that we could possibly have for E. Now let's prove that this is correct. First, for the if direction. If we have a Hamiltonian cycle from the original graph, we can turn that into a Hamiltonian path by effectively unraveling it. We take the cycle that starts and ends at E, and we replace that last part with an E' instead. Then we add S to the beginning and T to the end, and voila! We have a path starting at S, ending at T, and visiting every single vertex. Now for the only if direction. If we have a Hamiltonian path in our new graph, as we said before, we know it must start at S, as S has no edges going into it, and we know it must end at T, as T has no edges going out of it. The remainder of the Hamiltonian path therefore has to be starting at E and ending at E' just before T. If we take that and we attach E and E' back together again, we can see that whatever the last edge was taken to reach E' must also be an edge that could have been taken to E instead, which would have completed our Hamiltonian cycle. There's one reduction down. Let's do another one. What about going from directed Hamiltonian cycle to undirected Hamiltonian cycle? Here's our process. We're going to take the vertices from our original graph, and we're going to replace each of those vertices with a tiny gadget. It'll look similar to something you might have seen in some problems before. Every single vertex is going to be replaced by 3 vertices joined by 2 edges. One vertex will be the in vertex, one will be the out vertex, and one will be in between the two, connected by 2 edges, one to each of those other vertices. We're now going to reintroduce the directed edges from our original graph, but every single edge, instead of being directed, will simply have its endpoints determined by its direction. In this case, if the original edge was U to V, it will now be from U out to V in. We argue that if there was a directed Hamiltonian cycle in the original graph, there's now an undirected Hamiltonian cycle in the new graph. First, if the directed Hamiltonian cycle exists, we can replace every single edge in that cycle with 3 edges. First, U out to V in, effectively the original edge, followed by V in to V mid and V mid to V out, traversing that vertex the rest of the way. This cycle will visit every single vertex in our new graph. The only if direction is a little bit trickier. Suppose we have an undirected Hamiltonian cycle in our new graph. First, we know that in order to visit some V mid for some vertex V, it must be in between our V in and V out nodes, or it wouldn't be possible to visit it at all. Because this is an undirected Hamiltonian cycle, we'll just assume that we're ordering our vertices such that V in comes before V out, so that it goes V in, V mid, and V out. If we start our undirected Hamiltonian cycle with some sequence of these, V in, V mid, and V out, we know that the next node that we visit has to be some other in node, say u in, followed again by u mid and u out, otherwise there'd be no way to visit the midpoint. We can continue this reasoning to see that in the process of creating this undirected Hamiltonian cycle, we must have visited all three vertices corresponding to each of the original vertices in our directed Hamiltonian cycle instance. And thus, we can just keep the edges in between some out node and some in node and use those to reconstruct a cycle in the original directed graph. Lastly, I owe you a reduction from earlier, from undirected Hamiltonian cycle to the traveling salesman problem. To remind you, the traveling salesman problem, stated as a decision problem, has some graph G and a number K. This K is the target for the maximum distance that our tour of all of these different vertices in our graph is allowed to have. We're starting with an undirected Hamiltonian cycle instance, which means we're starting with some graph that might not have all of its edges and has no weights on any edges. So we'll start by assuming that we're going to give every single existing edge a distance 0 in our graph, as seen here. Then we're going to traverse through and find every single possible edge that could exist, considering each pair of vertices, and if the edge doesn't exist, we'll introduce an edge with distance 1 associated with it. The total amount of time this will take will be n squared in the number of vertices, but that's still polynomial, so we're fine. Finally, k equals 0, so we therefore set our problem to finding out if there exists a cycle of length 0. The proof is fairly quick for this. If there is an undirected Hamiltonian cycle, then if we use that cycle in our traveling salesman problem, we'll find that it creates a distance 0 tour. Similarly, if we have a traveling salesperson problem cycle, then we know that every single edge that was used in that cycle must have a distance 0, which means that it must have been an edge that existed in the original graph. So if we take all of those edges together, we'll end up with an undirected Hamiltonian cycle. Hopefully this gives you a sense of why finding longest paths is much, much harder than finding shortest paths, as we've been doing previously in this class.